Welcome to another video. Today we're going over Hohmann transfers. This is a method used to get from one orbit to another, and it's the most fuel efficient way to do this. This is because it uses an elliptical transfer orbit to get from the initial to the final orbit. You can see in this image that the satellite is currently on the transfer orbit, and the transfer orbit is tangential to both the initial and final orbits. And this is a really key component that would allow us to save fuel. And this is illustrated in this photo. So imagine that you are on a circular racetrack and you have to get off. If you have to turn to get off like this blue car, you have to slow down a lot because you have to prevent your car from tumbling over. So you have to slow down to get off and you have to slow down to turn. But this pink car only has to get off and slow down. It doesn't have to change direction, and that causes it to not have to have a higher change in velocity. So higher changes in velocity in terms of orbital mechanics means you have to burn more fuel to change your velocity more. So if we have tangential changes in velocity, that means that the change in velocity is of a lower magnitude, so you're saving fuel. So in order to do a Hohmann transfer, we need to make three assumptions. The first one is that the orbits are coplanar. So you can't have one orbit like this and one orbit like this and try to get from one to the other. You would have to add a little bit of complexity to the Hohmann transfer. The second one would be that the orbits have their major axes aligned. They are coaxial. So if you can see in this image right here, this is the major axes of the first orbit, and this is the major axes of the second orbit. They are parallel and aligned. And if we have elliptical orbits, this is their major axes. They share major axes, so you can do it like that. You can't do a Hohmann transfer when your orbits look like this. So the third assumption is that there are instantaneous velocity changes tangent to the initial and final orbit. So right here you can see we've got two tangential velocity changes that are instantaneous. And this is, as I explained in a second ago, important for saving fuel. So to get from a lower orbit to a higher orbit, we need to point our thrusters in a way that gets our delta V to be in the same direction as the direction of travel. We want to be adding velocity to the system. And then to get from a higher orbit to a lower orbit, we want to point them in the opposite direction. So we want our delta V's to be pointed in the opposite direction of travel to slow the vehicle down, to have it fall to a lower orbital radius. So why is the velocity in the smaller orbit larger than the second orbit if we need to add velocity to get from the smaller orbit to the larger orbit? Well, this is because the additional velocity is actually contributing to the potential energy. Higher orbits have higher potential energy and lower kinetic energy, so the satellite will be moving slower, but it has a total greater amount of specific mechanical energy. So this is really well illustrated in this image right here. So at lower orbits, we have a lower amount of potential energy. So as you increase in altitude, the potential energy increases to a smaller negative number. And then you can also see that the potential energy is also decreasing. So the total amount of specific mechanical energy is increasing, even though your velocity and your kinetic energy are decreasing. And you can see that as you decrease in altitude, you need higher kinetic energy to keep your object in orbit, because orbits are simply objects in free fall that are constantly missing Earth as they fall around Earth. So you need higher speed to keep objects lower to the ground in orbit. So in order to do a Hohmann transfer, you need to first identify the initial and final orbits. You need to identify their departure and arrival points. So they are always 180 degrees from each other to cause them to be tangential to each other. And the third step would be to find the semi-major axis of the transfer orbit. So the radius of perigee would be the distance from the center of Earth to the closest point on the orbit. So that would be the center of Earth to the circular orbit, and that is radius 1. And the radius of apogee, RA, would be equal to the distance from the center of Earth to the largest point in the orbit, which would be R2 right here. And then the semi-major axis of the transfer orbit would just be adding both of them up and dividing them by 2. And then we need to find the delta V needed to get from the first orbit into the transfer orbit, and that is delta V1. And so the equation for velocity for elliptical orbits is this one right here. And then we can simplify this for circles, knowing that the semi-major axis is equal to the radius of a circle. So if we replace A with R right here, we can simplify it to be this. So that's why the velocity of the first orbit is equal to this, because it's a circular orbit, and the velocity of the transfer orbit, which is an ellipse, would be this. So right before the burn, the velocity of the satellite would be equal to this, and right after the burn, the velocity of the satellite would be equal to this, and that is the initial velocity on the transfer orbit right there. So then we need to subtract them and take the magnitude for the change in velocity needed to get from the first orbit into the transfer orbit. And then we need to find the delta V2, which is the velocity needed to get from the transfer orbit onto the second orbit. So the transfer orbit is an ellipse, so we use this equation. And then the second orbit is a circle, so we use this equation. And so just to reiterate, this value would be equal to the velocity right before the thrusters are turned on and the burn occurs. And this is the velocity right after the burn occurs. It is the first velocity of the second orbit. And so then you can find the duration of the transfer, knowing that the orbital period is equal to this, and then knowing that the orbital transfer only occurs for half of the orbit because they are 180 degrees from each other. So it's faster and it's only half of it. So you need to divide that equation by 2 and you would get this. Okay, let's do a example problem. So in this problem, they tell us the radius of orbit 1, the radius of orbit 2, and the specific gravitational parameter for Earth. So they didn't tell us which way the delta V's are pointing, but we can see that the satellite is in the smaller orbit. So we're going to be trying to get into the larger orbit. And in order to get into a larger orbit, we need to add a delta V to the system. So we need to point the delta V in the direction of travel. So that would be this way. And then we need the arrival point to be 180 degrees from the departure point. So that would be right here. And we can see that that is tangential to both of these orbits, and then we draw our instantaneous velocity tangential to our second orbit, and that would be like this. So that's delta V1 and that's delta V2. We've already identified the initial and final orbits. We've identified the departure and arrival points. So now we need to find the semi-major axis of the transfer orbit. So the radius of perigee would be the radius from the center of the Earth to the closest point of the transfer orbit, so right here, and that would be equal to R1, and then that would be equal to this. And then the radius of apogee is equal to the center of Earth to the furthest point, and that is the radius of the second orbit, so that would be radius 2. And then in order to find the semi-major axis of the transfer orbit, we need to add them and divide them by 2. And that's equal to this. Okay, so now we need to find the delta V needed to get from the first orbit into the transfer orbit. So we're finding delta V1. And in order to find delta V1, we need to find the velocity of the satellite right before the burn. So that's V1. And it's on a circular orbit, so we use this equation. And we're on the first orbit, so we use R1. So that is our velocity right before the burn occurs, and it would be the velocity without any interference. There are no burns, so that would be that. And then the velocity right after the burn, the initial velocity of the transfer orbit would be this. And we would use this complex equation because it is an elliptical orbit. And then that would be equal to 10.06. Okay, and then we need to subtract them and find the magnitude for the total delta V to get from the first orbit to the transfer orbit. And that would be in kilometers per second. But that's not our final answer. We're trying to find the total delta V needed to perform this maneuver. So we need to find delta V2 to get from the transfer orbit onto the second orbit. And so the velocity right before that would be on the transfer orbit. So we need this elliptical orbit equation. So we're going from the transfer orbit onto the second orbit. That's why we put those radiuses, those distances there. And for the initial velocity for the transfer orbit, we were going from the first orbit to the transfer orbit. So that's why we make sure that we put the right radiuses there. And that would be equal to 1.624. And this makes sense because the velocity right before you enter the second orbit is occurring at a higher altitude, so you would expect it to be traveling slower than when it was at a lower altitude. So the velocity on the transfer orbit was occurring at a much lower altitude. That's why it's much higher initially. So now we need to find the velocity right after the second burn, and it's on a circular orbit, so we do this, and it is the velocity of the second orbit, so we make sure to use R2. And then this makes sense also because the velocity of the satellite on the second orbit should be a lot smaller than the velocity of the satellite on the first orbit, and that is true because 7.669 is much greater than 3.081. Okay, so now we can find the total delta V needed to perform this transfer by taking the magnitude of both of the delta V's, and that would be equal to 3.848 kilometers per second. And this is our final answer. So as you can see, the spacecraft added 3.84 kilometers per second to its velocity, but it slowed down because of the trade-off between kinetic energy and potential energy. So the velocity on the second orbit was a lot less than the velocity on the first orbit, even though you were adding 3.8 kilometers per second of velocity to the spacecraft. So that's a Hohmann transfer, and in the next video I'll be talking about a little bit more complex topic of changing planes while using Hohmann transfers. And then I'll be talking about interplanetary transfers, which are a lot more complicated, but not too bad. So I'll see you in the next video.